51 n queens. The n queens puzzle is the problem of placing n queens on an n by n chessboard such that no two queens attack each other. Given an integer n, return all distinct solutions to the n queens puzzle. You may return the answer in any order. Each solution contains a distinct board configuration of n queens, placement where q and dot both indicate a queen and empty space. So let's see what this question is asking us. The question is saying an integer is given to us, so all we get as an input is going to be an integer. So this integer indicates the dimension of the chessboard, and also it indicates the number of queens that we have. So when the n is 4, we are going to have 4 by 4 chessboard, and we are going to have 4 queens. We should put these queens in a way that they cannot attack each other. So you might ask how queens can attack each other. A queen can go left and right, can go up and down, and it can go to like left diagonal and right diagonal. So let's write this down. Let's write down the information that we have. We need to know the queen moves. Queen moves can be left and right, which is going to be throughout a row, and it can be up and down, which is going to be throughout the column, and also it can be the left diagonal and the right diagonal. Okay, so these are the moves that queen can make. So let's see if this board is right. So we have the queen here. It can go all the way left and right. So the whole row is empty. The whole column is empty. So it cannot attack any other queen. So the whole left diagonal and right diagonal are empty as well. So this queen is fine. How about this one? The whole row, the whole column, left and right diagonal, they're all empty. How about this one? The whole row, the whole column, left and right diagonal are all empty. How about this one? The whole row, the whole column, the left diagonal, and the right diagonal, they are all empty. So this board is valid. And there is another way to do that, which is this board. And what we are going to do, we are going to return these two boards as a solution. As you see, it says we have an empty cell, we have the queen, empty cell, empty cell. The next row, we have empty, empty, empty cells, and we have the queen, and so on. And as you see, if n is 1, we have only one queen. To solve this problem, because we want to find different ways of putting these n queens on the chessboard, what we can think of is backtracking. Why backtracking? Because in backtracking, we recursively, we make a change, we call the backtrack function recursively, and we undo the change. So this way, when we move around these queens, we can make a change, and after we are done, we undo the change, so we have the empty board again, so we can check for other combinations. So one thing that we need to know for considering different combinations, we start from each row, and then we check like other conditions. We need to check 4 conditions. Checking 4 conditions, right? We need to check the row, we need to check the column, we need to check the left diagonal and left D, and we need to check the right D. I'm gonna say left D for left diagonal and right D for right diagonal. So we need to check these 4. What I'm going to do, I'm going to have a for loop. I start from the first row, I check the conditions, and if there is no constraint for the column and left and right diagonal, I'm going to choose where to put my queen. So before doing that, I want to show you something. So let's say this is the chessboard that we have, and it's n is 5, right? Let's write down here. So n is 5, and we have a 5 by 5 board, and these are the indices that we have. We just start from index 0 to 4, 0 to 4. what we know about the left diagonal, it's when we deduct the row index minus a column index, we are going to get the same thing for one diagonal. Let's do that. So 0 minus 0 is going to be 0. 1 minus 1 is going to be 0. 2 minus 2 is going to be 0. 3 minus 3 is going to be 0. 4 minus 4 is going to be 0. So as you see, all the way in this diagonal, when we deduct the row from the column, we are going to have the same number. Let's see if it is applicable for the other rows as well. So 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 1. So let's make sure for the other one. 2 minus 0 is 2. 3 minus 1 is 2. 4 minus 2 is 2. So as you see in each diagonal, the left diagonal that we are, when we deduct the row index from the column index, we are going to get the same number for the left diagonal. How about the right diagonal? We have the same thing for here, but this time when we sum them up, when I say, okay, 0 plus 4 is 4. 1 plus 3 is 4. 2 plus 2 is 4. 3 plus 1 is 4. 4 plus 0 is 4. How about this one? 0 plus 3 is 3. 1 plus 2 is 3. 2 plus 1 is 3. 3 plus 0 is 3. And as you see, for the right diagonal, when we sum them up, we are going to get the same number. So how can we use this to help us to solve this problem? What I'm going to do, I'm going to say, if I have a queen, let's say if I have a queen here at this cell at index 0 and 3, let's say I have a queen here. If I'm at row 2, right, and I want to put a queen here, and I check, okay, I don't have any queen, and let's say we have no queen in this column, we have no queen in this row, we have no queen in this diagonal. How about this diagonal? I check and to see the value of the diagonal at this point, which is going to be 3. And I already have it here, so I cannot put a queen here. So what I'm going to do, I am going to have 3 sets for every single one of these. I'm going to have a set for row, set for left diagonal, and set for right diagonal. So this way, whenever I put a queen, I will put the value of the row and column and left and right diagonal. I will save it somewhere. So for the next row, when I want to put another queen, I will check those values. If I have them in the set, I'm not going to put my queen there. So we are going to check this condition using 3 sets. And we are using the for loop, and for loop for the, we are going to use the for loop for the rows, number of rows that I have. So let's see how we can do that. For this, I'm going to say for backtrack, and just give the backtrack the row number, right? The row number is given here to the backtrack. I'm going to, before starting this, I'm going to have columns. I'm going to have a set for that. I'm going to have a set for left diagonal. Also, I'm going to have a set for right diagonal. And I'm going to be careful about the typos. And then I'm going to have a board that is an empty board. So let's have an empty board. I have a board here that is going to be an empty board, right? I'm going to have dot as an empty board. And n is the value that is given to me. And for anything that I have in range n, I'm gonna make this board, right? And then I'm going to call the backtrack function with index 0. I start from row 0, And what I'm going to do, I'm going to making the backtracking function, right? Let's see how we can do that. And I need to have an empty list for the result as well. Result is going to be an empty list, and I'm going to return the results as the answer. Let's build the backtracking function. I'm going to say if the row that is given to me is equal to, if the row that is given to me is equal to n, then I know I'm at the end of the rows, right? So what I'm going to do, I'm going to have a board. This is an empty board. I'm going to say for row in, I'm going to say valid board. I'm going to call this valid board. For row in board, right? For the rows that I have in board, I'm going to valid board. I'm going to append that, and we need to return in a specific order. It's going to be the string like that. So I'm going to append the dot join that row, okay? And after I'm done, I'm going to results dot append. I'm going to append the valid board to the result, right? And what I'm going to do, what if the row is not equal to n? I'm going to start from the columns. I'm going to say for columns in range n, I'm checking if the call that I have, if the call is in call, or if the row minus call is in left diagonal, or if the row plus column is in right diagonal. Any of these cases, if they are valid, what I'm going to do, I am going to continue. I just do nothing because it means we have a queen somewhere there, right? Otherwise, I'm going to say the columns that I have, I'm going to add the call, and then I'm going to the left diagonal, I'm going to add the row minus call, and I'm going to add to the right diagonal dot add is going to be row plus column, right? And then I am going to set the board that I have for this row and for this column equal to the Q that is given to us. Then I'm going to call the backtrack function for row plus 1. And now it's time to undo all the changes. So I'm going to say calls dot remove call left diagonal dot remove row minus call right diagonal dot remove row plus column. And finally, I'm going to say the board at row and that column, just put back an empty thing. Oops. There we go. What was that? Dot. Yeah, there we go. And after doing that, we are done with this. Let's run the code and see what we are going to get. Let me remove this from here so you can see the whole code, and we just need to make sure that we return at this point, and I think it seems fine to me. Let's run the code and see what we get. There we go. So the time and space complexity for these problem are both like factorial. And thank you.